Hi, this is Professor Cummings, and this is your class number one, or lecture number one, for DFMA. I know the slide says class, which say it's lecture number one. And in this one, we're going to go through an introduction of design for manufacturing assembly, uh, beyond that first intro video that I hope you guys all watch. This is going to have your first homework assignment, and it's going to also give you some understanding of what design for manufacturing assembly is and what the benefit of taking this course is. So let's see here. We have these are the topics we're going to cover. We're going to go over how design influences cost. I'm also going to go over some of the design manufacturing paradigms. And then finally, I'm going to go through concurrent engineering. Then we're going to start to explain design for assembly, design for manufacturing, and design for manufacturing assembly. Because there are three separate things that follow one another. And then how do you manage design for manufacturing assembly within an organization? And then some of the basic critique of a design that I would like for you to use in your project as well as as you leave this class. And finally, there's going to be some review questions, just a short list of questions that I want you to look at and consider as you after you finish this, just to make sure you know it. And if you have any trouble with those questions, you know, go ahead and rewatch the lecture and try to get a better grip on them because they're just basic questions from the lecture. And then finally, I'm going to go over your first homework assignment. Now, when I was an engineer at Delphi, an older engineer said this to me. He said, it's possible to manufacture most things that people can design. That's not the problem. The problem is you either don't have enough time, enough money, or otherwise enough resources. Which makes a lot of sense. And that's a pretty important concept, a pretty important rule of thumb to keep in mind. You can design and manufacture all sorts of elaborate and fancy things, but depending on the design, you're either going to take a lot more time to manufacture it. It's going to be a pretty expensive thing to manufacture, or you're going to need a lot of resources that may or may not be at your disposal. To keep that in mind when you consider your design. So it's more cost effective to design quality and efficient manufacturing practices into the product. Now, this is a concept that you see in Lean, see in a lot of Toyota manufacturing processes or philosophies. It's the whole idea of designing, these things actually into the process, designing quality in particular into the process. That's something that has always been a very important thing that has been part of the Japanese manufacturing culture, and in this case of our class, efficient manufacturing falls under that as well. It's just easier to design an efficient manufacturing process into the product itself. Don't make something that has to take a lot of elaborate and very meticulous manufacturing or very specialized manufacturing that you're going to have difficulty achieving those resources. Now, this picture here is just a triangle that I put together that we're going to see popping up in lectures quite a bit. Now, you see down here at the bottom, you have the design parameters, production volume, so things that you need to know when designing a product. As you move up, you have things like material selection, uh, primary processes, secondary and tertiary, and then finally assembly. So what this is just the entire design process laid out as a pyramid. And the reason I have them as a pyramid or a triangle is because as you go through your design process, as you go through this sequence, each subsequent step not only is dependent upon the previous step, but it becomes more restricted by what the previous step said. So as you as you got a problem presented to you, and you come up with the design parameters and how much you're going to need, the production volume, now you are a little more restricted in your material selection for a variety of reasons that we'll go into. Once you've decided the material selection as well as your design parameters, your primary processes, the type of raw stock that you're going to be able to use in the first place starts to go down. You start to get restricted. Once you've decided what that primary process is, any secondary processes and tertiary processes become even more restricted until finally you've got a very limited number of options in how you assemble the process. So if we were to break this triangle up, you could think of as the upper portion is your manufacturing processes, and the lower portion is your design processes, or are your design processes. And what we're going to look at now is we're going to specifically define what exactly is designing a product, as well as what it means to actually manufacture a product. And keep in mind that, in manufacturing, we've got different types of products here, or steps here of primary, secondary, and tertiary, and finally assembly. And, in design, we're only covering things such as design parameters and production volume and material selection. Now, I know that's a very simplistic triangle, but, it'll help you as far as our discussion, if we just think of it and know that I know there's more involved in design than coming up with parameters and a material selection. But for our intents and purposes, and for reasons such as cost and actual implications to the rest of the processes, we can break them down this way and be pretty safe in doing so. So what exactly is design? How would you define that? I mean, we use that word a lot. We say, we're going to design this product, we're going to design a process, we're going to design a solution. What exactly is design? Design is the process of creating a solution to a specific problem. Okay, and that's all it really is. You're coming up with a solution to a specific problem. I give you a problem, how are you going to get to work today? And you design a solution to that. I'm going to take the bus, I'm taking the train, I'm riding my bicycle, I'm going to walk. So a problem, how do you work after daylight hours? You know, Without any other type of source of light, you would be restricted to working just during daylight hours. At one point in time, we didn't have any ability to work past sunset. So how did we solve this problem? Well, depending on what point in time in history and how far you want to take this, the solution was a light bulb. Now, when we think of design would be the 1,000 attempts that Thomas Edison and his team used in order to create that final product, in order to be able to create this product. And all this in the middle was the design. This was all the things that he was taking into account that needed to go into creating that solution. So when you're designing, the designer has to understand all the parameters, required features, and end user desires. That's part of the design process. So, parameters meaning things like, are there certain material restrictions? Are there certain safety standards you're limited to? Does it have to have certain functional requirements, such as things as you're working within a certain temperature range, has to endure a certain type of pressure. If this is going to be in an environment where pressure is a factor, does it need a certain cleanliness to it? Also, end user desires, such as, does it have to be a certain speed, a certain type of height requirements, a certain type of weight requirements. So all of these things go into building the restrictions, the limitations that you as a designer need to take into account. And for most designers, they're pretty good at understanding this portion of design, being able to say, okay, I've got a product. What does my end customer need? What environment am I putting it in? And what are the requirements for it to be in terms of like regulations and standards? Now, you also have manufacturing. And you got a manufacturing engineer, what his role is to understand the manufacturing methods, the limitations of those methods and abilities and the application. So when to do something and when not to do it. When you choose one manufacturing process over another based on what you're trying to design. So you establish the manufacture and the assembly process. Your goal is also to try and reduce cycle time, which is a big thing when you're a manufacturing engineer. Reducing cycle time, you're selecting tooling, you're ensuring the process capability, making sure that you're making the product right and within certain quality standards, and you're also having to justify the expenses that you're doing as you make that process. No good in making a product that is going to not be able to pay for itself with the process that you made. And that is also why I started the manufacturing section at this point of the triangle. These are all the things the manufacturing engineer has control over, but as you can remember from the triangle, it's also restricted based on things such as what type of materials he would have had to, or he or she would have had to select, as well as any other design parameters that the design engineer had to operate under. So if the design engineer decided to make something that out of a special material that needed a certain type of tooling requirement, well, he's restricted in terms of what type of tooling he can use. If the reduction costs, if the designer designed something that required tons and tons of machining time or some sort of odd geometry that meant that they had to cast a part or had to do some other process, then well, he had to, that's going to impact how much cycle time and other types of costs, labor rates and uptime that's going to come on. And establish a manufacturing assembly process. Again, if you make something, if you require something to be 3D printed, well, guess what? There's only one way to make that, and that's through 3D printing. So all these things are things that the manufacturing engineer is responsible for, and he or she is completely restricted by what went on in the design process. Now, going through, exactly what is manufacturing and assembly? I know that's kind of a basic question, but let's go ahead and establish it. So, when we say manufacture, what do we actually mean? We're actually talking about producing components from raw materials. And, raw materials could be anywhere from, you know, raw plastic, off the shelf bar stock from metal supplier to castings or any other product that hasn't been processed by you yet. Assembly for our discussion is going just to be the joining of components to make the actual product. So now you've got completed and finished components that you're actually going to put together, and we're calling that the assembly process or assembly. Manufacturing can be things such as milling, casting, or even woodworking, carpentry. All those things are forms of manufacturing. And again, manufacturing is very vast. It could be several other things beyond that, but those are just some manufacturing processes. Things such as assembly, you've seen an auto car plant where they literally are putting the car together with nuts and bolts and welding and threads and screws and other types of assembly processes, adhesives and what. So you got completed components. Each one of those components in and of itself represents some manufacturing process, whether this is a stamping process or some sort of injection molded process. It came in as a completed part and it was bolted, stamped, welded, glued together in the assembly process. Now, oftentimes, what happens is that the manufacturing and design process are treated as completely separate entities. And what that has led to in the past, traditionally, has been called over-the-wall design or over-the-wall manufacturing, but over the wall. So basically what you're looking at this as is the design team, design team is different from the manufacturing team. The manufacturing team, and somebody comes up with the design, they know what a customer wants. Some salesman, comes up with the idea, and the product engineer says, okay, we will, or the sales guy relays them to the product engineering team, and they come up with some solution to what that customer was requesting. They draw it out, put it on a 3D model or whatnot, and send it over to a manufacturing team. This may or may not be in the same company, but oftentimes it can be in the same company. This could be some small design company and goes to a manufacturer, and the manufacturer just has to deal with it. They have a product, they have a blueprint, they have a 3D model, and they've got to manufacture to that 3D model. Part of the problem is that it can be a very expensive process. It may restrict the hands of a particular manufacturer, and you don't get a whole lot of feedback to your design that may have actually helped you out. There is some communication. There's sometimes the manufacturing team will say, hey, this is unreasonable or this is unusual, but you as the manufacturing team are still expected to just make that product as you have received it over the wall, barring any real issues with it. Some of the other problems with that, so we've got this pie chart here, and it's broken up into design, material, labor, and overhead. So some of the costs and expenses of manufacturing. Now, as you can see here, the design when it comes to actually making a product, whether it be a car or a pair of gym shoes, the majority of the costs, 60 to 80%, or in this case 70% of the cost, is determined during the design process. Remember the pyramid, remember the triangle. So the biggest part of the triangle was the bottom half, the designer portion of it, and that's 70%. 70% of the product cost. So 70% of the cost of your shoes, 70% of the cost of your computer, 70% of the cost of your stove, your refrigerator was established based on the design decisions that were made early on in the product life cycle. The next most expensive is the type of material that was used. And then there's the labor and the overhead, which are fairly small when you think of all the other expenses that are taken into account. So, just to put that into perspective, that's a lot of your costs are being decided at the bottom end of that pyramid. 90%, if we take the pyramid as I drew it, but 70% is just, what they call just the traditional product design portion. Now, how does that happen? Why does that get so much of the cost of a product? Well, it breaks out a little bit like this. Again, there's the bottom of that triangle. So it comes down to what the design engineer is actually responsible for, versus what we just looked at what the manufacturing engineer was responsible for. So the design engineer can determine what kind of material you're going to make, which means that you're going to know whether you're going to be machining, whether you're going to be casting, whether you're going to be, or how the machining process is going to work. It also can describe any preparatory processes or post processes that come because of the material. There are just certain materials that go through the manufacturing processes that need a lot more care and a lot more hand holding when they're being used in manufacturing. One that a lot of people I found when I was in industry don't really take into account is something like tolerances. Tolerances can have a major impact on the cost of a product. A lot of times engineers will design something and give it a tolerance just based on the previous design without considering the fact that by picking a very restrictive tolerance, they have just dictated a certain type of manufacturing processes. Not all manufacturing processes have the same level of capability to them. Some of them just aren't. You're not going to get the same tolerance trying to saw something as you would laser cutting it. Okay, or using a EDM machine, electro discharge machine. So the tolerance starts to go, as your tolerance goes up, you start to restrict manufacturing processes. And machining operations, inspection methods also start to become restricted as you start increasing or tightening tolerances. Another one is geometry. So things like radiuses, fillets, hole sizes, making things that are non-standard, non-standard sizes. If you go to Home Depot and look at drills, they come in a range of sizes. A set of drills are going to have a very predictable range of sizes. So if you pick something that's slightly in between two sizes of drills, in other words, a non-standard size hole, you're going to have to move away from standard size tooling. You've gone from a $2 drill to a $12 drill now because you're going to have to get special grinding and special manufacturing done on the tool before you can do the actual manufacturing of your part. Also, it can affect the size of stock that you select and even the type of material handling you use in order to pick the part up. Just because it might have an awkward shape and now you're worried about a safety issue. And then, it comes down to things such as the components themselves. Like when we think about the car example, the paneling, or any of the other components in the car, how you design them, how you have them work together and fit together affect the assembly process as well as the number of parts, which means the cycle time or the extent of your assembly process. So the design engineer has a lot of responsibilities, or maybe the responsibility is not quite the right word. Maybe we could call that implications of the design engineer. And here's just a list of processes. These are decisions that could be made based on a design that could actually impact how you manufacture. Putting a hole with a certain type of tolerance could be the difference between a boring process, which can be done on any type of turning machine or even a milling machine, to a honing process, which is a much more specialized process. You see this a lot in automotive industries. So they'll typically have a machine, and all it can do is do honing. It actually requires a certain type of honing fluid and a very specific type of tooling that comes in here versus a more generic tooling that you can get into a boring process. Deciding something has a odd or unique shape to it. So a net shape, which means now you've got to go into a casting process before you go into a machining process, and then finally maybe grinding and other things that you can do, versus say off-the-shelf bar stock, which is typically one of the cheapest ways you can manufacture something. On the other hand, there is a drawback to this as well. When you've got net shape, there's a lot less post-processing, secondary and tertiary processes. Since you've already removed a lot of material, you're not having to worry about doing quite as much machining. So, you got to weigh out whether or not it's worth it to go to net shape because of the extra cost of casting, the cost you'll save in the machining processes versus bar stock, where you're typically going to have to machine a lot of material away, but it's a cheaper starting material. Another thing is when you come up with really unique and odd shapes, now you're going to have to come up with very complex fixturing. The work holding that it's going to take to actually hold your component during the manufacturing and assembly process. These are some automotive parts. This is like some sort of a crank or a gear case housing. And this is an engine block. And of course, these odd shapes, have to have a fixture that is designed specifically to hold that shape, which means there are thousands and sometimes tens of thousands of dollars that just go into a fixture. When you come up with these weird and unique shapes. Not a big deal when you're making parts by the thousands. When you're making parts like the automotive industry does, you're going to buy this and this fixture is going to last for years and years, so it'll pay for itself. And over here you've got more generic shapes, and you can go to any Home Depot or uh, Harbor Freight and buy a vise, and actually hold onto a square component and drill holes in it all day. You know, a couple of $100 versus $8,000 or $9,000 for the other fixture. So those are all decisions or implications of a design decision that can add cost to a product or a manufacturing process that may have been unforeseen to the design engineer. So again, cost implications, there's implications through the materials, the amount of cycle time, direct labor, people who actually have to hold and handle the part, indirect labor, anybody supporting it, the water spider, the person who has to run your materials, special tooling, perishables, things like drills, mills, grinding wheels, invested capital. So if you come up with a design that requires a really specific manufacturing process, well, they may have to buy a machine or they're going to have to outsource that process in order to make your design. And then non-value added activities, things such as the part sitting in storage, the part going through shipment, part, even inspections considered a non-value added activity. So some of the design and manufacturing paradigms, just if we consider design and manufacturing as, kind of two separate entities, we already went over the wall, which is the most distance between the two. Then we've got the sign off, which is, manufacturing actually looks at everything after it's done and says, okay, we know what we're in for. Let's go ahead and do this. This would be almost the equivalent of what happens when you outsource a product. They're essentially just doing a sign off saying they understand what they're expected to make. Then there's the limited collaboration. This is a little bit better than the sign-off in terms of you're interacting with the manufacturer, designer interacting with the manufacturer. And what this is during the design process, let's say you're the design engineer and you come up with a feature and you're wondering, is that a reasonable feature? So you go talk to your manufacturing engineer and say, what would it take to make this rivet or you make this fillet? What would it take to get this surface finish where I think I need it to be? And that's when the manufacturer says, well, if you do this, that's your requirement, you're going to need a grinding process. But if you loosen that up a little bit, we can do that on the machine tool, in the machine shop. So that limited collaboration can help you make some decisions, but ultimately the designer is still the one in charge. and completely in charge and has the last say. And then you've got concurrent engineering. And this is the one that we're going to look at. This is a bit more of a general term that we're going to start to cover. It's the manufacturing and design actually work together from conception to product launch. So this isn't just going to a limited collaboration where you've already decided what the solution is and you are actually going through the process of designing it and you're getting some input here and there. Concurrent engineering means that manufacturing and design are looking at this product up front, together, and you're actually trying to do the design together to make it more manufacturable, which in turn will reduce costs. So what is concurrent engineering? It's a design philosophy that requires the stakeholders. Here we have the stakeholders and the design engineers engage in the design process. Now, that's an important word here, stakeholders. We'll define what that means in a little bit. Design engineers typically, they have their expertise, and it's typically not manufacturing or assembly. Now I understand that, a lot of times everybody has an ME or an MET degree, so we all know a little bit about both sides of the wall, but this is speaking of typically if you're a design engineer, you generally aren't going to have a whole lot of manufacturing experience. And if you're a manufacturer, you generally have moved away and you're doing a lot more manufacturing than design. Again, as we said before, 60 to 80% or 70% to the pie chart of the product cost is determined by design decisions. So concurrent engineering addresses the manufacturing process, manufacturing issues early. Again, that is very important. That is one of the beauties of concurrent engineering. You address the stakeholders' concern when you're still in the conception phase, or well before you've nailed down the design. So more concurrent engineering. Now, there's several types of concurrent engineering. This is not just a synonym for design for manufacturing engineering. So concurrent engineering, that word stakeholder comes in again. So concurrent engineering engages the stakeholders of each level of the product. And that can be design for assembly, design for quality, design for service, design for the environment, and even design for disassembly, or design for maintenance. And oftentimes this is referred to as DFX, design for X, where X is that stakeholder. So that's all concurrent engineering is. It's just an umbrella term for all the types of engineering where you're considering designing your product around a certain stakeholder's concerns. In this case, we are going to be looking at design for assembly, where that's the primary or one of the primary stakeholders, and design for manufacturing, where that's also a major stakeholder. So this would be a format of, or a small diagram of concurrent engineering, where everybody from the design side, the customer, the product engineer, sales, is interacting with the manufacturing side. So manufacturing, quality, and product manager. We could even put in other people such as, the line workers and other people who might actually have to interface with your product. But the point of this concurrent engineering model is here. Everybody's got some sort of an input to how this product's going to be built and how it's going to impact them. So design for manufacturing. It reduces the costs, reduces the number of steps, number of operations. It selects the more economical processes. So manufacturing can tell the person up front, the designer up front, what are some of the processes that would probably be best suited that he could design for. Helps to understand, to limit scrap, can immediately eliminate process variation or minimize the effects of process variation. Again, that's establishing tolerances, understanding how parts might be supported, being able to detect where something might have some vibrations, at least during manufacturing. Certain things, are going to have an issue if you manufacture them certain geometries. Increase your throughput. Make something. One of the things you could do is make something so it actually is held in a fixture without having to be released and taken out quite a bit. So it gets handled a lot less and reducing the amount of cycle time. So all these are things that design for manufacturing actually does. Design for assembly, very simple, reduces the number of assembly operations, makes easier to assemble and to perform, or assembly to perform. So it's got this little diagram here of a part with multiple little components, and then making to a part where they've actually built some of these components pre-assembled or made as a unit. So we've eliminated all these little nuts and bolts and dials that probably aren't going to move relative to one another and may actually just be assembled and made rigid and turned them into one component. In other words, combining. So we reduce all those parts down to this limited number of parts. Easier to assemble, faster to assemble, less parts to keep track of. So the goal is to address the costly manufacturing and assembly issues in the design prototype stages of a project. So again, back in that early part of the project, the most expensive part of the project, that 70% is when you're trying to understand where the manufacturing issues are going to come from. So if you can reduce the amount of costs established early, that means you reduce all the costs through the manufacturing process for the life of the product. Manufacturing and assembly supplements the skill set of product design. So you're not taking over, the manufacturer isn't taking over the design process. They're just giving you enough information to know that the product, what's going to make it easier or not so easy to manufacture. So some of the things to think about in terms of how this affects costs. Well, obviously, I've bolded some of these and made them red. Simplicity, creating liberal tolerances has a direct impact on costs. Uh, Easily processable materials, avoid process restrictiveness. In other words, if the manufacturer has enough flexibility to put something on various machines, that could actually cause a little more nimbleness in the process. And there's several others: standard materials and components, standardize the design of a product. The one part number doesn't have a bunch of unnecessary changes from the next when they do changeovers, and a few others. Some of the advantages, again, you can see here 39% of it is actually the time to market. One of the biggest advantages, because you're reducing a whole lot of the issues from the design, as well as reducing a lot of the manufacturing assembly costs is being taken out. The design for the manufacturing process is a lot faster, a lot more efficient. Another one is the quality benefits, the manufacturing time itself, and then the two others, assembly time and the part cost and count, are other advantages. But you need the biggest one is actually getting things to market and making those decisions a lot faster. So what the process looks like, when you actually implement design for manufacturing assembly into a process. Well, you've got the concept of your design, and then you go to design for assembly. Look for any suggestions that might impact your assembly of your process. So in other words, you're looking at basically how the parts put together, things that need to be combined and eliminated. Then finally, you consider the material selection. Okay, and this comes next because you're getting a lot more, getting a significant boost from the assembly that's going to impact other things further down. All right, so your material selection, which is also, you can assemble any kind of materials, so think of it that way. You would actually have another review, any tweaks to your design. Then you go into design for manufacture, where you're actually looking and reviewing the manufacturing processes themselves. Okay, and again, once you've come with your materials, you've kind of restricted yourself, but again, you're trying to consider, is there anything that you can change still at this point in the DFMA process where you could, before you commit. And now you finally get to the prototype. So general rules of design, for those of you who haven't had a design class yet, this might be seen by some people who haven't had much of design. And good rules of thumbs, I'll let you see these in the slides, but some I wanted to point out. Design for standard tooling. That's a common thing that I talk about in my manufacturing classes. Don't come up with funky shapes just for the sake of having them. If you're going to have a weird shape, a non-standard tool shape, make it be a good reason. Otherwise, go for the standard. Avoid sharp corners. Again, stress razors is one reason. Another one is they're not always that easy to manufacture. Design for minimum setups. Avoid parting lines if you're doing castings. So again, there's several of these in here. Those are some of the most obvious, the ones that jump out at me right away. And again, you'll have access to slides. So when you're going to put DFMA into an organization, how do you go about this? So one is managing your DFMA. Whoops. So managing your DFMA. So that means, you're going to have to organize the team and get everybody to engage during the entire process. So this is going to be a pretty big cultural change for any organization, because a lot of companies are used to the over-the-wall processing. You also want to make sure everybody's trained in DFMA so they know what's expected of them, why they're doing it, why things are going the way they're actually going, and what's ultimately the goal of DFMA. So the first thing you want to do is get a good team together of people who all understand the product, all understand or their relative part of the process as a stakeholder, and then be able to understand that they know what that process of design for manufacturing assembly ultimately is. Now, some of the risk of concurrent engineering as a whole, including design for manufacture or design for assembly, is it is a time-consuming job to manage a team of people. People aren't just there to do one thing as design for manufacturing. Like I said, the design engineer is going to have other projects. The manufacturing engineer has to support the production. So, you're going to have to organize these people, and there is a lot of consumption there. So it's a downside. You also have to deal with personality. That's nothing unique to this, though. That's anytime you've got people working in groups. It's expensive to bring teams together. Every time you bring a team of people together in an organization, they're being paid. And so when you put 6 people together for 1 hour, you basically have lost an hour of 6 people pay, whatever that might be. So it can be a pretty expensive endeavor. You know, Lost time of people not performing their other tasks, lost time of members to perform team tasks. So when your manufacturing engineer is in this team, he's not doing she's not doing her job on the floor. And then there's the overall resistance to change. So you've got a design engineer that may not be too keen on being told that, they might need to change something because a guy in quality didn't approve. So that's going to be part of the culture shock. Now, how do you critique a design proposal? So as you start your project, you're going to have to critique it, and you're going to have to be able to come up with some intelligent ways of attacking it. So you have several questions that you want to ask, certain ways you want to look at it before you go into the actual start of the redesign. One is, can the total part count even be reduced? Can the components be standardized? Are the tolerances too restrictive? What operations are really required? Is it easier, cheaper material processes for the same result? Are we using some expensive grade of steel when a cheaper grade would do? Can the number of setups be reduced? You know, will special tooling be required? There you go back to those standard sizes and standard and weird geometries. And what are the consequences of making certain changes? Another very important question. What are the consequences of making certain changes? How do you measure your success? So your goal is to reduce cost. I'll say cost and time, but time typically works into cost. So cost can be expressed as reduction of number of components, the number of processes. Making a much simpler process is better than a complicated process, less chance of error, less capital investment. Reduction in the amount of material. So not having to spend as much on material costs or reducing a lot of waste. You can have a or less expensive process and a faster process. So when you do your project for the semester, this is your goal. So some review questions. So here we are. So what is the role of a design engineer? When you think of this process, what is the role of the design engineer? What is the role of the manufacturing engineer? And can you describe what over-the-wall manufacturing or over-the-wall engineering is? And how is over-the-wall engineering different, different from concurrent engineering? So answer some of those questions. Go back and review, check out your slides, and if you're having trouble, go back and review a little bit and see how this works. So your homework. So for your homework, I want you to read chapter 1, product design for manufacturing assembly, which is just kind of an overview. Then on Blackboard, there's a few case studies I want you to go through. And then write a paper, no more than 2 to 3 pages, that summarizes the article. That's the first half of your paper, or first section of the paper. Second half of the paper is critique how they apply design for manufacturing assembly. So, they're all based on the same topic. Just give me your insights based on what you've read in the book and what you've gotten from this video. How are they different from one another? How do you, or excuse me, how do you critique what they've done? What do you think of their process and their application? Well, this is Professor Cummings, and this is a little longer than I had expected, but hopefully it was giving you a lot of insight into why we're doing design for manufacture. Um, Again, you get my office hours. Give me a call, email, and if you any questions. Um, Again, and like I said, just submit your solution into or your paper into Blackboard. All right, thanks for watching.